So if you all got the notes, the final project is not due today. See, no one turned it in, so it looks like so hopefully you're not secretly panicking or something. But it is due a week from today. So hopefully keep working on that as you need to. There is a homework due on Wednesday, and you know, it's. I know some people come to me saying they're trying to do it in Java or in something else, and it's much easier to do it in MATLAB. The learning curve is not that hard. I suggest you do it in MATLAB. If you're having trouble debugging the question 2, where you have to write the program, I really suggest try going through each line on the command line and seeing what happens. You can just do that in MATLAB. It's very easy to kind of debug. They're only should take less than 10 lines inside a for loop. So just go through each line, go through 1 or 2 iterations of the for loop, make sure it's working like you think it is, and then transfer those into your function. So that's the easiest way to debug it. The matrix I gave you as input is probably too big to see what's going on, but you can try running on a much smaller matrix. You know, use, say, the matrix X that I gave you, or one of the matrix I gave you for another part as your input, or just create a smaller subset of the big 1A. And try running on that and see what's going on and make sure it works. And that's the easiest way to debug it. If you find that the size of the matrix you're trying to add or you're trying to subtract or multiply don't work, you probably mistyped something from the notes. A lot of people complain about this, so just try writing it and keep seeing what you mistyped until you get it to work, and you'll probably find that you can get the dimensions. So it's probably the easiest way to do it. So it's a little confusing dealing with matrices. Trust me, it's better to do it in MATLAB or Octave than just about anything else, where it's a lot harder to deal with these sorts of things. Hopefully you're all, if you haven't used MATLAB before, hopefully you're really kind of getting your first taste. If you are, hopefully this is not too hard. All right. We're going to continue talking about graphs, and last Wednesday we talked about Markov chains, and today we're going to kind of apply them towards understanding the PageRank algorithm, right? So before this class, who had not heard of the PageRank algorithm? Okay, so most people heard of it. So who kind of knows how the Pagerank algorithm works, you think? Kind of some idea. Okay, so a few of you. So hopefully I'll talk about some extensions at the end. So hopefully you still learn something new. So you get a different perspective on it. So the Pagerank algorithm is a way of understanding the importance of nodes in a graph, and in particular, applying it to the graph defined by the World Wide Web, basically the internet and web pages, assigning importance to web pages. And so this has had a really big impact on the whole tech industry. In particular, this is the algorithm that they basically built Google around. It allowed Google's search results to be much better than anyone else's. So before I get into how PageRank works and how it relates to Markov chains, I'm going to start by kind of giving a history of how search engines worked. So before I start, so did anyone see there was a talk in the Ski Institute by Prabhakar Raghavan a week or two ago. Did anyone see that? Yeah, so that was do you think it was an interesting talk, or were you way back and you couldn't see anything? So he has kind of been an adjunct at Stanford for a while, and co-wrote a book with Rajiv Motwani around the mid-90s, right after Google started, and Rajiv Motwani was the advisor, the PhD advisor of Larry Page and Sergey Brin, the guys who invented PageRank and started Google. And then he helped start Yahoo Research, And so it's had a big influence on the web industry. And he talked about kind of a lot of the issues that go on why search engines work the way they do and so forth. So I believe the talk's actually online. It might be an interesting talk to go see and get a similar perspective on this topic and some of the other things that we talked about in class from someone who's kind of been there and had a hand in the development of all this. Okay, so the basic idea of how a search engine works, well, its goal, what a search engine essentially does, how you interact with it, is you make a query and it returns a list of, say, websites or kind of documents on your computer. And it's kind of, your interaction with it is just through what's called an inverted, is just through what's called an inverted index. And so an inverted index is something where it kind of lists all possible things you would search for. So say if you search for the word pi, then the inverted index will have pi pointing to, so it's going to point to a list of so it's going to point to a list of web pages that have the word pi on them. And hopefully it's going to be sorted in an order, so the more pages related to the word pi, more related, more interesting about it, come first in the sorter cycle. Okay, so when you search for this, the search engine should return you this list of pages, but you can't see them all at once, so it usually returns something like the top 10. The first 10 pages is what you see. Like if you search on Google, it'll list like 10 links on the page, and then you can hit like next page to see the next list of links. So, back when search engines were getting started, you would pretty often have to go onto the next page and kind of keep looking for stuff. Now it's really rare that people look beyond the first page. It's even pretty rare. Less than, I think, there are studies like less than 1 or 2% of all searches, people actually scroll down to see what's beyond. Usually the first few links are really sufficient, and it's really rare for people to go to the next page. So really, only the top ones of these matter. So an inverted index, though, is just this thing where for every keyword, it has already stored this list of pages. Okay? And so it's a way of it can very quickly return the list of pages. It doesn't have to do more calculations usually. Okay? So there are certain things like if you say apple pie, so instead of just pie, Google probably has cached a list even if the search was apple pie, because that's common enough. Okay? But something like 30% of all searches, though, are not things that they have cached. And they have probably 100,000 keywords, sets of keywords cached. The most common 100,000 sort of keywords. But still 30% of them are beyond this. And for that, they kind of look at each keyword, they return the list, and then they have to kind of combine these lists together on the fly. And this takes a little bit longer, but it's still somehow based on these lists I have for the individual keywords or this set. And sometimes if you search for something, like if you're trying to spell, so this was I remember when Google was going around talking to colleges around 2000, in the early 2000s. So the most popular search then was for Britney Spears. And so, but most people didn't know how to spell actually her name. It's kind of an odd spelling. And so there were like 10 different variants of Britney Spears that were all in like the top 100 of the searches. And so all these different variants, they all pointed to the same list. They kind of figured out they're all looking after the same thing. So there are a lot of weird combinations of letters, and they'll probably try and autocorrect them. And they'll use something like the edit distance to find words with similar things, and then they'll return that list. So even if you type in something random, it may try and generate something on the fly, or it may try and autocorrect to some other term and say, did you really mean this list? And so it'll get to that. So this list is kind of something that is pre-built. The key to a search engine is how do you rank these lists? How do you get this top 10? Okay, so this will be what we'll need to be talking about. I'll talk about MapReduce on Wednesday, and we'll kind of talk about how you would build one of these inverted indexes. Okay, so the building of this is not too hard once you have MapReduce, but the ranking of these pages is a real difficulty, and that's what PageRank does really well, or it's part of what goes into that. Before I go on, I should just remind you of an announcement that the room here is booked next Wednesday, so we can't have class in this room. It's in 3105. Unless people really want to have it outside, we can try and have it on a hill. Do people really want it outside?
It's nice enough.
It should be a really nice day on Wednesday. Who would really want it inside? Okay, so, okay, I think I'll try and do it outside. I'll post something to the mailing list if I can get something to work. So I'll try and do it on one of the hills outside the MED building. That'd be a good opportunity to do this. So also, if you've taken kind of my models of computational or massive data class, or you know about MapReduce, you know, we may not all fit in the 3105 lecture room. It holds like 40 people in it. So if you don't want to see this lecture, I posted videos on the web page from when I gave the lecture in this class last year, and also a different overview lecture that you could see instead if you want to. But I'll still be giving the lecture anyways. So it'll just be in a different location. Okay. All right. So don't come here next Wednesday. I'll see if I can leave a note, but I may be pretty busy next. Okay. So how do we determine which of these pages is most representative of this keyword? Okay. So how this worked initially is through is by using cosine similarity. Okay, so remember this. The idea was you turn a page, which was actually, it was a string of words. Okay, so I turned this string of words into this model called the bag of words. And so this was like a multi-set. I kept track of which words were on this web page. And I could do this with k-grams instead of words if I wanted to. And so then you think of each page is, there was some vector, so we call this page 1, this was vector v1. And so it had for v1 I, it had the number of times word I on the page, right? So for each word I, it kept track of the number, and most of these were 0, right? So this was a vector, and then the cosine similarity was kind of essentially the angle between these vectors. So you normalized this vector, and you took the dot product between this vector and the very simple vector with this keyword, where this just had a 1 for pi and a 0 everywhere else. So it's just the dot product of these, and so the more times this page had the word pi on it, the higher it would rank, versus as a fraction of all the words on the page. Okay. So this was kind of how search engines were first built. So, but this lecture, the first part of this lecture will kind of be a story of of these approaches and then how these approaches fail. Okay, so I'm going to ask you, how did this approach fail? Like, what was wrong with this? So, are you confused how this worked? Do I need to show an example, or is this?
So is this algorithm ranking a page which has more a number of words a higher rank?
No. So it first. So if you remember the cosine similarity, it first normalized the vectors and then took the dot product.
Okay.
So it had. So it had two vectors. This v1 for page 1, and it had the vector for pi, which was 0, 0, 0, and then 1, and this is for the word pi. And then it basically the cosine similarity is of vector pi and v1 was equal to the dot product between v pi, which is already normalized, and then the normalized version of v1. Okay, so it doesn't matter how many words are on there, it matters the fraction of times that the word pi occurred on this word. Right, so I've normalized out based on the size of it. So I made both of these have to be unit vectors, and you can think of them in some high-dimensional space. So this is v1, this is v pi, and this happened to be on the pi axis. Sounds like a good axis to be on. And then the dot product is essentially, I projected it on here, and the dot product says the length of this projection. So if pi occurs very frequently along here, it's going to have a similar angle to here. So the dot product is kind of, there's a isomorphism with the angle between these two vectors. That's why it's called the cosine similarity, essentially the cosine.
So it's probably bigger pages with not much content. Since,
Yeah.
I mean, you don't really factor in, since the percentage, you don't really care how much things are on the page, you just care about the percentage. So if I had pi day versus a whole article on the history of pi, I might hit pi day more than, I might have a higher similarity to pi day than the history of pi.
Yeah, that's right, right. So if someone just wanted, so people realized that these search engines were being used and that people navigated the web by searching for stuff. So they said, well, if I want to show up in the search engine for the word pi, because people keep searching for the word pi, then I'm just going to put the word pi over and over again on my web page. It's going to say pi, 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 right? So maybe that's what you want, but probably not. You probably want something on the history of pi, right? So, and in fact, so, you know, this was probably before people were really making money off of advertising. They were just trying to get people to look at their web page. And so they would do these tricks where they would say, I'm going to have whatever I want on the web page. It can actually be about Britney Spears, whatever. But then at the bottom of it, I'm going to copy the word pi like 1,000 times and put it in a font that's white, so you can't even read it. So you don't even know it's there. Make it really small. No one even knows that the word pi is there when they visit the web page. But if you search for pi, you end up coming to my web page, and I can show you, you know, the Britney Spears pictures. I don't know, whose pictures would you look at today? Emma Watson, exactly. So, very good, very good. So this turned out not to be great. It didn't really tell you about the content of the page. So it turns out that there's really a lot of, in this ranking, in the ranking here, in the ranking of these pages, which really turns out to be the magic. Anyone can build this inverted index if they have a big enough servers, whatever. But the ranking is really determines how good the search engine is. And this kind of determines some magic, right? You kind of say, if the word pi occurs more than 1,000 times and there are only 10,000 words on the page, they're probably trying to spoof something. So I'm going to actually not use this page. I'm going to have some different heuristics I use to try and say, what is a good ranking? And maybe I kind of know that a lot of the pages that have the word pi in them, they also have other words. So pi is related to other words like apple with pan, like delicious, like recipe. So you find these associated words, and then instead of using just this pi vector, you use a vector that has these other words in it as well. So then you kind of know what the content of pi should actually be about. So you kind of change the search in various ways, and a lot of this is kind of black magic. They still kind of use something like the cosine similarity, but they'll do some extra heuristics on top of it. Okay? But you still have this kind of vector representation that you can do this, but this algorithm still, even if you did these magical tricks and just used some version of this, there's still a kind of, in retrospect, kind of obvious hack you could do to try and get on the top of these rankings. Anyone know how this kind of next level of trick works? Yeah.
Copy your search for pi, then copy your first page and your page.
That's right. So here's this next trick. So what you do is you search. You go to the search engine, you search for pi, and this gets you some these 10 top pages. You get the content of these. You copy these pages at the bottom of your web page and make it in the same color as your background. You copy these to your page, and then whatever kind of magic that they use to do this similarity ranking, because it ranked these pages well, it will now tend to work your pages well. And you can kind of iterate this process a bit, and you can move yourself up the rankings this way. And so these pages start doing this as well, right? And so this was, for a while, this was kind of the state of the art that people were doing. This was the next step past cosine similarity. And there's kind of like how later on there was this fight between spam detection and spammers. They tried to fool it. There were these spam web pages or these trick web pages people were trying to use, and search engines were trying to create better ways of ranking these pages. And this was kind of a trick that was really hard to beat if you just use something like some version of the cosine similarity. Okay, so then the next idea that happened is that people said, well, we're going to use a crawler, okay? And so the idea of a crawler is that it's kind of it's a program that automatically kind of randomly walks around the web. So so it kind of goes to a web page, and then it clicks on a link, and then goes to the next web page, right? So I know sometimes when you're bored, you're kind of doing this yourself, right? And this was kind of the idea. So you go to these web pages, and so when they were building these indexes, they needed these crawlers anyways to find which web pages they were going to put in the index. They needed to get these lists. So they were already doing these crawlers, but when you have this, that means you have more information. You know, if I got to this web page, how did I get there? Right? So then you can look at these hyperlinks. So a hyperlink is like a word that's been highlighted that when you click on it, it takes you to another web page, right? So this word usually, if this word said pi and it linked to my web page, pi.com, then it probably meant that pi.com was about pi. Someone linked to it, right? So if pi went to this page, then this page is probably associated with pi. So instead of just looking at the context on the page, I can look at what the hyperlinks said when they were pointing onto this page. Okay, so this is hard to spoof because now I can't just change the content of my own page. I have to change the content of someone else's page. So this was harder for these kind of spam web pages or even non-malicious people just trying to promote their own web page to kind of beat. You actually needed to get linked to from someplace else. But people still got around this. They would make lots of these dummy web pages that would just link into their page. And so they would try and get the crawlers to go. You can kind of tell the search engines, send the crawler over here, because my page is interesting, and they would put it in their list. And so you get them to go there, and they would all link to your pie page with the word pie, and it would get promoted, and then it would just have some pictures of just Emma Watson on it instead of pie, right? It's not what people want, right? So this was kind of the next idea, but it was, you could still kind of spoof it by creating these other web pages. And so when people are really interested in promoting their page, they would actually go and do this. And there are services you could buy to kind of get your web page ranked higher. There still exist these services, and they would use tricks like this, where they would build a bunch of these dummy pages to do this. The kind of the next idea, and this was kind of going on simultaneously, was there were these meta web pages called indexes, and the examples were like Yahoo and LookSmart. So I don't know if any of you remember LookSmart, but so actually Yahoo is still around. It's still actually a very heavily used web page. And what these did is they actually went and cataloged a bunch of pages they thought were interesting. They had people who'd go through, and they actually had people browsing the web and saying, these are interesting web pages. So actually, Yahoo started because, again, two grad students from Stanford, they were kind of early access to the web, and they just kept one web page with a bunch of hyperlinks of pages that they liked. And this grew and grew. People would go to their page to find other interesting pages. So now you have like RSS feeds, and you have blogs, and you have Twitter and Facebook for you to do this. But this was, someone just had this big web page called Yahoo, where people went and found these other web pages. And so this wasn't really a search engine, but this was an alternative to using a search engine. And this was, some thought, a viable alternative. They thought search engine would never work as well as human catalog pages. But search engines could also use these. These pages were somehow more trustworthy. They were more important. So you could say, if there was a hyperlink from Yahoo and from LookSmart that both said pie and point to my page, that's probably more trustworthy than some random page I've never heard of. So these were, so the idea was, an important an important web pages, an important web pages hyperlink was worth more than kind of a random web page, right? So these were kind of important, and maybe there were some other important web pages. Maybe Stanford.edu back then was trustworthy, and so if they linked to something, it was probably worth doing. Well, so one of the downside was these indexes, they were trying to make money, and so one of the way they did this is they would allow people to pay them to link to a page. This is not so radical now, but this was kind of a very controversial idea at the time. LookSmart was actually much more into this model, and a lot of their pages, when they were at their peak, were actually based on people had paid them to link to their page. And this worked for a while, but some people thought this was going to be the dominant way people browsed the web, because these search engines were failing to these people, kind of spamming them with these fake pages. This kind of was going on until around the time Google came, right? So Yahoo, to some extent, somewhat works under this model still. They have, if you go to the Yahoo front page, it's a very kind of, there's lots of stuff going on, and you can personalize it to your own taste, but it has lots of links, and they kind of curate those links for you. They're kind of under this model, but they also, people still use search off of that web page a lot. So now we can start to get to PageRank. And so PageRank is built on two kind of main ideas. And the first one is kind of here. So idea one. So a web page is important if it's linked to by other important web pages. So the idea of PageRank is to say which web pages are important. It's not really necessarily saying the relation with a certain keyword. That still needs some sort of magic based on cosine similarity and some other tricks. But it's saying, I want to link to pages which are similar to my keyword and are also important. Right? So Yahoo pointing to it would kind of be like, yeah, that's probably important, but maybe someone paid for that. So I don't want to let Yahoo get the money for someone paying to link to that page. Right? So I want to determine myself whether it's important. And so PageRank is trying to do that. So important web pages, if important web pages link to my page, then my page is probably also important. So important web pages, hyperlinks worth more. This leads to, so this kind of defines the importance of the web page I'm trying to understand. And the second idea is that, so I didn't want to rely on someone else's definition of importance. I wanted to determine this automatically. A web page is important if a random surfer would likely visit it. Okay, so the idea is, if you are randomly going to pages around the web, if you're likely to find a web page, if you're likely to go to it by just going to a web page, clicking on a link, then going to the next web page and clicking on that link, and keep doing this, if you're likely to get to a web page, it's probably important. So this is kind of how these crawlers worked, right? So these crawlers were already kind of doing this. And we already thought that if there were these more important web pages, they probably told us more than these random web pages. So this should be able to get around the idea of these spammers. They couldn't just make up a web page that did nothing but link to a fake page about pi. It had to actually be important for that web page to mean something. So we somehow need to understand the idea of this random surfer. How would they, how do we do this? So one way would be to just run a bunch of these crawlers and just count how many times that they visited a page. If they visited a page a lot, it's probably important. It turns out this is a pretty inefficient way of doing this. The web is very big, and a crawler may not reach a web page. At least in the when Google is being built, it may take them, if you update your web page, it may take them like a month before they re-index it. Now that they may do it overnight if they know it's been re-indexed a lot. But this was a little bit too inefficient to just use the counts of the crawler and kind of noisy. The idea was to use the techniques for Markov chains, right? So we wanted to build, so in order to do this, the idea of importance is what's called a Pagerank Vector, and we wanted to build a graph of the web and think of it as a Markov chain, and then the converge to vector will be the PageRank. Okay, so so the web is going to equal a directed graph where an edge from P1 to P2 is if P1 links to P2. Right? So you can have a crawler go to a web page P1 and find all the pages it links to P2, and these are the edges in your graph. So now to define the graph, I can use all the machinery from Wednesday to define a Markov chain on top of this graph. Okay, so then I define this big, and all I really needed was this probability transition matrix, and that meant if I was on page 1, I'd essentially randomly choose one of these page 2s that were linked to go to. So this defined this probability transition matrix. Okay, and so then I can say that Q star equals P limit as n goes to infinity of P to the n for any Q0. Right, so for any initial importance, guess of how important the web pages were, maybe this was uniform overall web pages. I can take this probability transition matrix I've built on the web. I can take it to the limit. As n grows, I keep multiplying by this matrix, and I get this Q star. This is what's known as the Pagerank vector. So it's not quite. I'll talk about ways you need to fix this a little bit. But so you build this directed graph on the web. You think of it as a probability transition matrix, and then you take the limiting distribution of the Markov chain defined by this probability transition matrix. And this is essentially the Pagerank vector.
So don't you need a web crawler to develop your graph?
Yeah, right. So you need the crawler to crawl it once, but then you don't need to keep running it to count the number of web pages. So you could do that. So there are a couple reasons why you wouldn't do that. So first of all, a crawler is a bit more efficient, is a bit more inefficient. Whenever it does, it goes to that site and it asks whatever server has that web page to go and get all of the content of that web page, some of which is hyperlinks. Okay. If I went and I sent the crawler and I already gathered the hyperlinks, then I can just store essentially that column of this probability transition matrix. And then I don't need to revisit the web page. I can just reuse the column I have stored. And so they went in and did this, and then you could think of running a crawler on the graph.